Swayam Prabha. Digital India. Educated India.
Hello everyone, in this lecture we are going to talk about the shortcut or the approximate method of calculating the number of stages and the optimum reflux ratio in this process. So, this is something known as based on 3 persons, the Fensky, Underwood and the Gilliland equation. So, the Fensky equation talks about the minimum number of the stages. The Underwood equation talks about the minimum reflux condition, and using this together you have the Gilliland correlation which helps you to determine for the given number of stages or given reflux ratio what would be the number of stages, or alternatively what would be the number of what would be the reflux amount. So, all of you know that when you Fensky equation is for the case of minimum number of stages at the condition of total reflux, right, and Underwood equation tells you minimum reflux ratio at infinite number of stages, right. So, these are the two possible extremes actually. So, this is Gilliland correlation is connecting this above two, connecting the Fensky and Underwood equations to calculate the number of stage or the reflux ratio. Okay. So, first we will talk about the Fensky equation, then the Underwood equation, and finally the Gilliland correlation. Before we go ahead, I also like you to highlight or give you some information regarding what we mean by key components. So, the components whose concentration is specified in the distillate and the bottom, right. So, these are called the key components. Next is something known as the light key and the heavy key. So, light key is more volatile of the key components, and heavy key is the less volatile of the key components, right. So, there is something also known as non-key component. So, this is all other components in the system except key components. Okay. Now, let us look into the situation for the Fensky equation. So, distillation with total reflux, right. So, let us say you have the distillation column like this, and you have the reboiler, right. You have total n number of stages excluding the reboiler, and again you have the total condenser, right. So, the total the top vapor fraction is, let us say, is written by like this, I mean YBI and whatever number of components that we are having. Similarly, the liquid phase can be written down as X dist. Not confuse you, let us write only AYI, YAI. Similarly, the bottom is X A N, right. It's not AI, it's A1. The top tray composition, top phase vapor and all. And for the reboiler, let us write down as YAR. Okay. So, XAN is the liquid phase composition that is going into the reboiler from the last stage. YA1 is the top vapor composition that is going into the total condenser, right. So, for binary component, for binary distillation, this is true. I mean, the Fensky equation also holds for distillation at total reflux VLE, vapor liquid equilibrium in the reboiler right, tells you that YA by YB at the reboiler is equal to alpha, that is the relative volatility at the reboiler. This is true for the reboiler. R denotes the reboiler, and this is true because from definition we know that alpha AB is YA by XA divided by YB by XB. This is something by definition we know. Right. So, now making a component mass balance around the reboiler, and then we try to use those equation to substitute YA and YB and all those things. So, L X A N, I write L as L bar because this is the stripping part, V bar YAR plus B into XAR. This is around the reboiler. So, or I can write VYAR is equal to L bar XAN minus BXAR. So, this is if I am trying to make a mass balance or component mass balance around the reboiler, right. So, for total reflux we got in the reboiler, of course, we have YAR is equal to XAN. Everything, the mass or the mole fractions that is in the liquid state that is entering the reboiler is getting completely converted to the vapor part into the system, and similarly this is for component A, right. Similarly, for component B you have YBR is equal to XBN isn't it? That is true. Now from here we can write, so let us call this from these two equations, I mean using these two equations, you can write YA by YB in the reboiler is equal, I mean this equation we already have. Now this can be written down, I mean this equation can be written down as XA by XBN is equal to alpha R XA by XB at the reboiler. This is we are equating from the above equation, isn't it? YAR is equal to XAN, isn't it? Now similarly for stage N, I can write YA by YB nth stage is equal to alpha N XA by XB at the nth stage. This is possible, isn't it, from the equation of the relative volatility. And we have this YAN is equal to XAN minus 1. I mean I hope all of you know the type of nomenclature we make for the trays, right? So the liquid that is coming from the previous tray is getting vaporized and is becoming the the vapor fraction is equivalent to the liquid composition from the previous tray. So this relation always holds, isn't it? So I hope I should write down how the 1 to this stage numbering is done. So if you have any particular stage, the vapor leaving, I mean the vapor composition leaving from that stage is equivalent to the liquid that is coming to that tray from the previous stage, isn't it? That is how the numbering is done, and that is why these relations hold. Similarly it holds for BN also. Now you can continue to do the same thing. So we can continue to do the same thing for n minus 1 stage, right? So we will get what we will get. I mean this is something we can continue to do for any stage, not for n minus 1 stage, n minus 2, n minus 3 like that. So what we are getting, so from the n stage what we are getting, XA by XB for the this one we are getting for n stage, isn't it? This is something we are getting, and this we are actually equating as YA by YBN, isn't it? Now on the right hand side this can be written down as XN alpha N alpha R XA by XBR, right? Similarly I can continue this. I can continue this for n minus 1 and for any stage actually. So for the n minus 1 stage we will get XA by XB as n minus 2 is equal to alpha n minus 1 alpha n alpha R. Everything can be equated to the reboiler, right? So we can continue up to top, continue till the top tray is reached. So we get XA by XB in the distillate is equal to alpha 1, alpha 2 dot 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 alpha n minus 1, alpha n, alpha r. It can be related to the reboiler. Right. So if we try to define, a sort of the a geometric average relative volatility, right, based on the minimum number of stages, something like alpha AB is equal to alpha 1, alpha 2, alpha 3 and minus 1, alpha n, alpha r to the power 1 by n mean. So this is the geometric mean based on the for the minimum number of stages in this case. So we can write XA by XB in the distillation, in the top fraction as alpha AB to the power n mean, isn't it? XA by XB at R. So where n mean can be written down as log of XA by XB distillation divided by XA by XB at R divided by ln alpha AB. You can also write this. You can also write this n mean as in terms of the fractional components, that I can also write this as dxa by dxb. D is the distillate rate, right, divided by b. B is the the part of the reboiler, right. This is also possible. So you can write this L mean based on the fractional recovery of the system, right. That is also possible to write in this case. How? Let us also work that out. So for the key components, I can also write that the fractional recovery of component A, the key component A, in the distillate is given by, let us say, FRA distillate. Then what do we get? I can write dxa distillate is equal to this is something I can write fractional recovery into ZA FA. Similarly, I can also write BXAR is equal to 1 minus FRA So F is the molar feed flow rate and XA is the mole fraction of A in the feed. And also please note that BXAR is equal to BXA at the bottom. So similarly, I can write the same equations for component B, right? So if in that case I can rewrite my N mean as FRA in the distillate, then FR B in the bottom divided by 1 minus FRA distillate 1 minus FRA, sorry, this is FRB, this is writing 1 minus B, FRB in the bottom divided by ln of alpha AB. This is the n minimum in terms of fractional recovery, right. FRB at the bottom is of course the fractional recovery of component B at the bottom. So, for binary systems, this is for multi-component systems, and based on the key components we can write this equation. So, for binary equation, this equation, I mean for binary distillation, this equation leads to as n minimum ln xa by 1 minus xa at the distillate divided by xa by 1 minus xa at the bottom So, this is the n minimum. So, this is known as the Fensky equation, right. So, where the number of trays or the minimum number of trays based on the total reflux condition can be estimated on the knowledge of the this relative volatility or some gross relative volatility of the mixture, and provided the top and the bottom compositions of the key components are known. Now, let us now quickly move to the Underwood equations. So, in the case of the Underwood equation, which is applicable, so this Underwood equation is applicable for the minimum reflux condition, right, and of course the natural consequence is that for minimum reflux you have an infinite number of stages. Right. So, again let us draw the simple distillation column and mark the streams. Right. So, always we have a total reboiler, and here right. So, this is stage 1, this is stage n, let us say arbitrary number of as arbitrary stage j. So, the vapor that is coming in is V, and let us Vj, and let us call this as Lj, okay, and this D and Xi distillate. The bottom part, if you are taking out anything from the bottom, we can call this as B, Xi bottom. Okay. So, let us try to do a mass balance in the enriching part. Okay. So, we try to write down a mass balance in the enriching part. So, we get y I j plus 1 V mean, right, is equal to x I j L mean plus xi dist, that is day, right. So this is for the enriching section. You have the minimum flow rates of your liquid and the vapors, and around the intersection of the top and the bottom operating line, if you recall that graphical construction where you have you remember that Q line, right, and then when you try to draw the stages, right. So this is something you are used to and familiar to doing, right. So then we had the Q line, and at the Q line then we said the feed stage has to be passed, right. So at the intersection of that is how we segregate as the top and the bottom section of this column. So at the intersection of the top and the bottom section, top and bottom part of the column, we have xi j minus 1. So please note, j represents the stage and I represent the component as this, right. So this is, you can call the feed tray or the composition of the pinch tray, right. So similarly I can write y, there is also this phase equilibrium, j plus 1 is ki xi j plus 1 from the phase equilibrium. So if I combine this equation, combine the mass balance equation, combine the this intersection of the bottom and the stage and all this, as well as combine the equilibrium relation, if I combine all of these equations, I get this one, isn't it? Now let us say for a multi-component species with respect to a reference constant, I can always write down that Ki is equal to alpha I with respect to a reference value. This is always possible. With respect to a reference component, I can write down the relative volatility alpha and to find out the equilibrium constant Ki. This is always possible, right. So doing this gives me from this equation that I have V minimum yi j plus 1 minus L minimum divided by alpha I k ref, right. This is something I can write down is equal to dxi distillation, right. And from here I can write down as 1 minus of this quantity, this is something I can just write down. So this is possible to get from here, isn't it? Of course I have to write down as V minimum also here if I try to put the bracket, right. This is possible to write from this equation, and subsequently I can also write this V minimum as yi j plus 1 is equal to d, divide that, I can also write multiply top and bottom with alpha I, so it's alpha I minus L mean by V mean k ref. So these are all algebraic steps, and I hope all of you are following, and that's why I'm doing a little bit quickly. Now summation of V mean yi j plus 1 will give you V mean, because summation of all the vapor phase components will lead to 1, isn't it? And this will be equal to the summation of alpha I dxi at the distillation divided by alpha I minus L mean by V mean K ref. So this is the summation. So for stripping section, same equation can also be obtained. I am not doing that calculation here, but for stripping section you can also get the same equations. Let us write that as using bar, just to segregate the stripping and the enriching section, right? Instead of distillate you will get bottom. Right. So generally this alpha I is not equal to the alpha I bar as well as K ref in the stripping and the enriching section is not equal, right? So let us define two quantities, phi as something like L minimum by V minimum K ref. Similarly, phi bar is equal to L minimum. So this is like this ratio fractions in the stripping and the enriching section, right? So from here, I mean, if I combine this phi and if I reproduce this phi, what I get is this V minimum. For the enriching section I have alpha I dxi at the top divided by alpha I minus phi. So this is for the enriching section I have, and for the stripping section I have V mean bar, I mean minus of V mean bar as summation of alpha I bar bxi at the bottom divided by right. This is something we have for the top. Now if you add these two V means, what you get? So V mean minus V mean bar is equal to the summation of these two quantities, isn't it? I mean alpha I dxi distillate divided by alpha I minus phi, right, plus alpha I bar bxi bottom as alpha I bar minus phi bar, right. So now if you relax this idea that alpha is not equal to alpha I, so if you relax this criteria and say that okay, look, that we are going to consider a sort of uniform alpha for the entire domain. So if you relax the criteria and say that alpha I in the enriching section is same as the alpha I in the stripping section, and this phi in the stripping and the enriching section are same, then we get V mean minus V mean bar is equal to summation of alpha I dxi distillation plus the top b xi bottom divided by alpha I minus phi. This is something we can do. So this is the first Underwood equation to obtain phi. And generally how do you obtain this? V mean minus V mean bar is using the material balance. So let us say from overall material balance, we know that Fzi is equal to dxi at the top plus B. This is something we know. So we can write V mean minus V mean bar is equal to, let us say, Vf isn't it? And what is this delta V? So difference of the vapor flow rates in the enriching and in the stripping section is equal to the amount of vapor present in the feed, right? So delta V in the feed divided by the F is nothing but 1 minus Q. All of you are aware of what do you mean by Q. Q is the ratio of the amount of this liquid component in the feed. So 1 minus Q is V. So delta V feed is equal to 1 minus Q into F, isn't it? So that's how you will get your this difference. So delta V is nothing but the difference of this quantity. So from here you can relate back and you can find out, I mean, F is known, Q is known, right? So from this equation, I mean, essentially relating this equation, I mean this one with this one will help you to find out what is your phi. And once you find out what is your phi, so from the previous case, I mean, this is essentially the second under root equation. So the second under root equation, right? So this is the first under root equation, this is the second under root equation. And then once you are able to calculate your phi, you know already this relation that V mean is this quantity, right, divided by alpha I minus phi. So you already know what is your phi from this, and then you can work out what would be your V minimum. So if you know your V minimum, you can also calculate your L minimum, which is V minimum minus T, right? So in this way you can work out what would be your reflux ratio to the problem, isn't it? Reflux ratio is nothing but L by D. So that is something you can work it out. So using these two relations, so now you know that from the Fensky equation we can find out the number of stages for total reflux, and from the under root equation we can calculate out what would be the minimum reflux ratio for infinite number of stages, right? So the Gilliland equation is actually a chart, though I am drawing it in a schematic, but you can also find it anywhere in your you just do a Google search. This is something you will be able to find out. So on the left hand side it is n minus n mean divided by n plus 1, and at the bottom you have L by D minus L by D at the minimum condition divided by L by D plus 1. So this starts from 0 to 1. So this is scaled with respect to 0 to 1 for this case. So this is the Gilliland relation. I mean, this chart gives you a relation of these quantities, right? And of course you understood that from the n minimum is something to be obtained from the Fensky equation, and L by D minimum has to be obtained from the under root equation at the criteria of minimum reflux or infinite stages, and a Fensky equation is for the case of total reflux. So if in your problem, if the number of stages are specified, then using this chart you can work out what would be the reflux ratio. If the reflux ratio is specified, then you can work out what would be the number of stages, and you see that these two cases correspond to the the extreme cases, right? For example, if you are working with the case, I mean, if you are saying that you want minimum reflux ratio, then the x coordinate becomes 0, and naturally the y coordinate turns out to be almost infinity, that actually approaches to infinity. It's not actually to 1, it actually approaches to infinity in fact, right. So which tells you that the number of stages is infinity in that case. Again, in the case of number of this number of stages to be minimum, right, if I select this number of stages to be minimum, the curve reaches to a situation where it is almost tending towards infinity. So maybe I should draw a slightly better curve here to represent the infinity part, something like this. It doesn't actually touches the baseline or the y-axis line, right. So this also tends towards infinity, this also tends towards infinity. Okay, so I hope all of you have liked this class on this is actually a shortcut method of calculating the number of stages or the reflux ratio, whichever is not specified, based on the idea of the Spensky and the Underwood relations, and which is coupled together using this Gilliland correlation. Thank you for listening and your attention in this class.